of material heritage that involve understanding various materials and techniques used in creating art and its conservation and preservation. The division is also involved in conducting lectures for disseminating knowledge on the subject. It gives me great pleasure to introduce our speaker, Dr. Rajesh Agnotri, scientist, Birbal Sahni Institute of Paleosciences, Lucknow. His presentation on radiocarbon dating, fundamentals, advances, and case studies. The talk will cover preliminary details of 14 dating application in the field of archaeology in general, with a few case studies. It gives me a great pleasure to introduce our speaker, Dr. Rajesh Agnotri. He is PhD in chemical and isotopic studies of sediments from the Arabian Sea and Bay of Bengal, Physical Research Laboratory, Ahmedabad. Dr. Agnotri received several honors and prestigious awards like Krishna Medal, Gold Medal by Indian Geophysical Union, Hyderabad, India, National Geoscience Award 2013 given by Ministry of Mines, Government of India for making outstanding contribution in geo-environment studies by Honorable President of India, late Shri Pranab Mukherjee at Rashtrapati Bhavan. He will be talking about radiocarbon dating, fundamental advances and case studies. The talk will cover preliminary detail of dating applicability in the field of archaeology. Now, I welcome Dr. Rajesh Agnotri to start his presentation.
Thank you, Dr. Mamta, and good afternoon, everybody. And I hope I am audible to everybody. Let me begin with thanking the INTACH for giving me this opportunity to share what we are doing at BSIP. I am basically, as been introduced by Dr. Mamta ji, that I am supervising a radiocarbon dating and isotope characterization lab at Birbal Sahni Institute of Paleosciences, Lucknow. It's a very old research lab of Department of Science and Technology. And in this talk, I will cover, as you can see from the title, some fundamentals and advances, especially from conventional radiometric method to AMS method, and few case studies, and particularly some case studies pertaining to which you can call it as important for INTACH Conservation Institute, and what you people are doing. Maybe it may be relevant with you. And beforehand, I have to say that it may so happen, right now I am seeing 41 participants are there. If you have some questions, you can put it in chat box or you can write it down. After the talk, I think we will have enough time to discuss about that if I can address some of those. I don't claim that everything I know, but some of the information which I'll provide in this talk may be very primitive to some sector of audience. So I apologize for that, because I have to keep this at a very elementary level, at a layman level, so that everybody can appreciate what we are doing. So I'm beginning with somebody. I'm beginning with thanking my lab members. In this photograph, as you can see, the old lab, the technical officers associated with it, some of them have been retired now. Some young colleagues are there who are my students, like Sanjay and Nikhil, PK Singh, Palji, Bhaskaran is a glass blower. The radiocarbon lab has all the paraphernalia, people who have visited it. And please let me know, Padma ji, if any audio problem is coming in between.
We can hear you loud and
Okay.
clear.
Okay.
Yes,
Thanks.
thank you.
So I am beginning with preliminary introduction of the carbon isotopes. And I suppose that everybody, I mean, including really everybody, knows that carbon on our planet Earth is the basic, the signature of the life. We all have, the carbon-based life here. Okay. And the carbon as an chemical element, it has 3 isotopes. Okay. Okay. So the carbon has 3 isotopes and abundances are given here. The carbon 12 has 98.9% abundance. Carbon 13, which is also a stable isotope. This is having 1.1% abundance. And the most important, carbon 14, this has very, very low abundance. You can see here out of 10 to the power 12. Carbon 12 atoms, we have likely only one carbon 14 isotope in this. Is there any problem? Yes. So I hope everybody is able to see the my screen, right? The cartoon.
Yes, sir.
Okay, fine. So you may be wondering that why these isotopes are different. Let me just brief it up that any element is actually characterized by the number of protons which it holds in its nucleus, and mostly in same number of neutrons are also available in the nucleus. So carbon 12 has, for example, 6 proton and 6 neutron, whereas carbon 13 has this thing, 6 proton and 7 neutron, and carbon 14 has 2 neutrons extra. So when you increase the number of neutron, as you know, is even though a neutral kind of particle, neutral fundamental particle, but it adds instability to the atom. So when the carbon has 2 extra neutrons, it becomes unstable and it becomes radioactive and it decays back. What do you mean by radioactive? With time it will decay and again it will go back to its own original form. So how they are produced? In the upper atmosphere, around 500 kilometers from the surface of Earth, this thermal neutrons, this low energy neutrons which are coming from the galactic cosmic ray as well as solar cosmic ray, they interact with our atmospheric nitrogen particles as the reaction is showing. And one neutron, when it reacts with one element, one atom of nitrogen, it converts into 6C14 and one proton. And the moment carbon 14 is produced, it immediately gets assimilated in the food cycle, because this gets reacts with the oxygen, and first it makes CO and then CO2, and CO2, as you know, is a very famous gas because it is mainly absorbed by the photosynthesis by the plants on the ocean surface as well as on the land surface. So when in this cartoon, as you can see, it becomes, the carbon 14 becomes the part of the global biogenic cycle. So it gets absorbed by plants as well as all the other animals, as well as, I mean, you can say all the humans, because we are all eaters of biomass. We either eat carbon dioxide. I mean, you may be wondering, some people may think that we are exhaling the carbon dioxide, but we are eating the oxygen and other thing. But what I mean to say here, that you are eating the carbon dioxide in form of its photosynthetic product like glucose, monosaccharide, polysaccharide, etc., food items. Okay. So the fundamental of the carbon 14 technique is this: as long as any animal or the floral life, the vegetation is alive, continuously it exchanges the carbon, because you eat food and that gets digested, and then you release the carbon in form of CO2 during its respiration. So the input and output, mostly you can say they are in equilibrium. So the carbon 14 content of any living thing remains constant, and it remains in equilibrium with the atmosphere as long as the person or animal or the plant is exchanging the carbon very well. Exchanging means signature of life, that it is live. And as soon as the material dies, the exchange stops. And when the exchange stops, this carbon 14, which was accumulated in the body, it has to decay, and it decays back to where from it came. What I mean, carbon 14 will decay back to nitrogen with emission of a beta particle and some energy. And this is very important reaction here, because this decay of carbon 14 is not affected by any physical or chemical properties of anything. It just depends on its initial amount. And this decay reactions are actually known as steady state reactions, and this decay is governed by only a decay law. I'll come to it, with a half-life of 5730 plus minus 40 years. So after knowing this simple thing which I just told you, that carbon 14 decays with a very well constant half-life of 5730 plus minus 40 years. This person, Willard Frank Libby, he was from Michigan, USA, and I have already explained that what the carbon 14 decay means. After applying this technology for dating the biogenic material, this person, I think he made this kind of experiments and discoveries in 1940s or 50s, and very soon, I would say in 1960, he was awarded with a Nobel Prize in chemistry. And the committee recommended very highly, and with this particular famous quote, which I want to read: seldom has a single discovery in chemistry had such an impact on thinking in so many fields of human endeavor. Seldom has a single discovery generated such wide public interest. So this was from the committee. And this actually provided, this opened up the avenue for absolute dating or scientific dating of archaeological materials, because in most of the applications in archaeology, we are interested about the history, which is for few thousand years, particularly last 10,000 years or so, or at the most past 50,000 years. So with the given half-life of 5.7 kilo year, the carbon 14 provides a very good tool to archaeological works, as it provides a time span of 50,000 years, which is actually governed by its half-life and the detection limit. In the future, if the detection limits improve with the technology, then we may go up to 55 or 60,000 years. But at present, 45 to 50,000 year we can go with this technique. So again, I'm trying to re-explain with some cartoon that whatever is happening on the planet Earth, on the continental landmass as well as in the ocean, carbon is always in exchange with the atmosphere. That's the key. And when that material like tree is cut from its root, means it dies, or animal dies, or any person dies, then the exchange stops and the current 14 decays with a decay law. Here you can see the activity of any particular time is can be computed by its initial amount A0 with into e to the power minus lambda t. Lambda is a decay constant, and decay constant is actually can be computed from its half-life. So it's a very simple mathematical equation, not very complicated, and very accurately the decay constant is computed. So, so here, what I have shown here, there is a steady state of production of carbon 14 in the upper atmosphere stratosphere, and then there is a loss of radioactive loss of carbon 14 atoms on the surface of Earth and in the oceans when the carbon gets buried, and everything is governed by very simple mathematical equation. And for any purpose, I can tell you on the surface of sea, at the sea level, normally the carbon 14 production rate is only about 1.8 to 2 atoms per centimeter square per second. So this is the level of production rate which is computed by scientists, and these production rates can be changed temporarily, sometime especially. These are some other intrusive research subject. I'll come to this if it is required later in my talk. But and then I just want to give you a glimpse that how it is all governed. We are in our Earth is part of our solar system, where Earth has its own geomagnetic field and Sun has its own magnetic field, and we are in balance of it. So, and apart from this Sun and Earth, we are in a celestial space where a lot of cosmic rays keep coming from our galaxy. They are called galactic cosmic rays. So basically, we have two types of sources. One is Sun and one is the cosmos. So the galactic cosmic rays and the solar cosmic rays, these two types of cosmic rays, their proportion actually governs this production rate. If there is any imbalance in our magnetic field, shielding effect, you can call it, and if the energy which is coming from the sun or even the cosmos, we generally believe that it is all constant. Okay. So this type of picture, what it shows some supernova explosions, etc. In sun, something gets burst out, then production rate can change. Or even on the earth, there are some processes which humans are carrying out today. Today means in last, let's say 100 200 years, because of our development or urbanization. These factors, particularly in the upper picture, you can see this coal burning for power generation. This is adding a lot of old carbon, which is devoid of any carbon 14. Because as I said, if anything is older than 50,000 years, it is almost as, you can treat it as blank. So all this coal or the fossil fuel, diesel, petrol, which you are burning in your vehicles, this is all devoid of carbon 14. So these emissions which are providing CO2 to the atmosphere, but this CO2 is totally devoid of carbon 14. So these factors are actually diluting. This is called Swiss effect. These are diluting the carbon 14 content in the atmosphere. And then I think everybody may be watching TV these days, and there is a huge talk about this another possibility of nuclear bombing somewhere in Europe or somewhere else. We don't know. So this is a very interesting anecdote from current 14 that due to the fossil fuel burning and the coal burning for the power generation purpose, scientists were getting worried that even, I mean, the carbon 14 is so low, already 10 to the power minus 12 level, and it is getting further diluted by this Swiss effect, the fossil fuel and the coal burning effects. So people were worrying that maybe this carbon 14 very soon will be low, very, very low. It will be very difficult to, use it any longer. But sometime, you do something and something else comes. As we can see, during 19... okay. After 1963, I don't know, maybe let me take you to the history, because today these days are similar to those days. You can relate it to that. After the Second World War, the World War stopped when Germany got defeated, but there started the ego clash between the former USSR, Soviet Rus, and United States of America, and that thing is everybody knows as a Cold War. I don't know, many people might remember those days, particularly after 1950s or 60s. So in those Cold War, all these countries developed a lot of nuclear weapons, and this so-called nuclear bombs were tested on the open ground also. India also tested later on underground. So these days we have a lot of nuclear power all around the earth, but in that major nuclear powers are with US, United States of America, and still with Russia. So the peak of this nuclear bombing came at around 1963, and this nuclear explosion provide an extra source of carbon 14, which is not produced naturally at the top of the atmosphere. So that you can that carbon 14 is called as a pulse or bomb pulse. So this bomb pulse is known to be coming on planet Earth during 1962, as you can see from this plot. And after that, because international treaties came and all, some here and there, some countries like France and all, China sometime, they tested their nuclear weaponry, but not that much compared to USSR and USA. So this curve started getting down. Okay, here you can see this curve is going down, and this is happening. Why? Because most of this carbon gets absorbed on the surface of ocean, because surface of ocean, produces phytoplankton productivity. On the surface of earth we have a lot of vegetation, so all this vegetation absorbs this CO2 in form of photosynthesis, so this gets absorbed. So earth has its removal system. Okay, but ironically, what I want to tell you, that this bomb pulse, when it came, people thought that now carbon 14 is all going to be wasted down. But contrary to the thought, this bomb pulse came as a blessing in disguise. Okay, for scientists at least. And using this bomb pulse, now we can date some very, very important objects in our life, like they have on every medicine there is a expiry date. In these kind of applications, wine dating, or old rice dating, most of the eatable things sometime we want to have drinking or eating, they have to be as old as possible. Rice and wine are famous example, but who can say that when they were made? Current 14 can tell. In drugs, if you are using some biogenic sources for making substrate, then carbon 14 can come as a tracer, very reliable tracer for finding out adulteration by petrochemicals, because petrochemicals are cheap and easy. Biogenic products are costly. Most of the time it is done. So carbon 14 got lot of applications because of this. Now, I hope everybody got that, what in nutshell, that what carbon 14 dating is. So now it is my duty, since I am from BSIP, to tell the narrate the story of carbon 14 coming to the BSIP. And after getting the Nobel Prize in 1960, I think BSIP was very wise and visionaries were there. They created a carbon 14 dating lab. Way back in 1974, it became operational. Okay, there is a document published in Radiocarbon in 1978, which shows our old, some people from INTACH, they have visited our lab. They have seen this benzene preparation line and the liquid scintillation counter. In the left-hand side, you see this. This is the benzene preparation line, where any organic or inorganic material, you have to combust and take out the CO2 and purify it, and then you have to convert it into the acetylene by reacting it with the lithium. I'm in this talk particularly, I'm not going into the details of this. This is a pure sheer chemistry here, what we do. What you need to know here, all the carbon needs to be converted, whether it is organic or inorganic, it needs to be converted into either 1 ml, or maximum, if you have sample amount is enough, is 3 ml of benzene. Benzene is C6H6. It's a very stable liquid. And then after making the benzene, we quantify it. I mean, we weigh it very precisely, and we add some chemicals which are called scintillators, and we keep it for let's say 1 week or so to die out some short-lived radioisotopes which can be co-produced along with these reactions. And then we have here this liquid scintillation counter, where in this kind of vials, the pre-weighed and scintillator added, the benzene is kept, and the decay is counted in several set of samples along with the standard. So with this kind of, this is called conventional radiometric dating. Okay. With this kind of method, only bulk amount of sample, means large amount of samples can be dated, and they can be dated really very well, like peat material, wood material, charcoals, bulk sediments, sediment soils, and inorganic shells, carbonate shells. You can hydrolyze them with the acid and take out the CO2, and you can date them. Suitability you have to check. But unfortunately, with the conventional radiometric method, some of the important materials like macrofossil of a small size. Basically, here what I mean to say that even though they are called macro, but they are actually sometimes micro, like agricultural grains which you get from archaeological sites, a very small piece of organic matter, straw, husk, or some small piece of textile, leather, rope, paper, and bones. Bones are often found, in India or everywhere, bones and teeth. but very rarely they have been dated. They have been utilized for dating because this the other method which I am going to talk about, the AMS method, uh, was available to very few people, or you can say none. So this is the instrument I am going to talk about. This we don't have yet. This is the smallest instrument. Otherwise, accelerator mass spectrometry is very big, very big. At least it requires at least 3 big size rooms. But this is a small compact type of AMS which is used for carbon 14 dating. Still, you can see it's very big. You need a very big size room. And let me just tell you the history of this AMS. In 1998 world, you can see only these places, particularly in United States and some parts of Europe. Uh, they were there, or one dot you can see over India, which was in the Institute of Physics, Orissa, but this facility never worked actually. Some parts of China or some Japan had, or Australia. But AMS, today's world, in 2017, this figure, number of AMS have increased quite a lot, particularly in India also. In Physical Research Laboratory, Ahmedabad, where I did my PhD, they have a brand new AMS operational since 2019. And also at the same time, IUAC, Inter-University Accelerator Center, they developed their own accelerator, and they coupled it with the mass spectrometer. I mean, they also have now AMS behind the JNU campus. So we have 2 running AMS at present. We don't have AMS, but I'm going to tell you that what we have. But all in all, it's high time for a country like India. We should have several AMS lab, as you can see the dots from Europe and America. It has its own significance and applications. People who are interested, I can come back this to later. But how do you compare the beta counting technique and the AMS method? This is there in very short. I can tell you, in AMS method, you can date even 1 milligram of carbon if you have a 0.5 milligram, even less than 0.5 milligram of carbon you can date very easily, because it directly counts the atom. I have to go little faster because time is running out. If anybody is interested in this kind of slides, I can come back to this later. In nutshell, AMS is million times more sensitive than the beta counting method. But here I want to warrant you, that doesn't mean that it is superior in AMS is superior in terms of giving some other kind of age. It is not like that. If you have enough sample, both liquid scintillation counting method as well as AMS should be able to give you same age, almost same age. The only thing what will happen with AMS, uncertainty will be much smaller compared to the beta counting method. So to keep our aspirations alive for AMS dating, for everything, the instrument I had shown just few slides back. But when I came to BSIP in 2015 September, and then I started working about this, we had only beta counting system. So in 2017-18, we could get sample preparation units for the AMS, because in AMS you don't need benzene, you need only 1 milligram of graphite powder as a sample. From any sample, organic or inorganic, whatever carbon is there, you have to extract it and you have to convert it into a solid graphite powder on the activated iron powder. So this is the setup which we have at BSIP now. And as you can see, this is mainly the graphitization unit. In a day, easily 7 samples you can process, 7 graphite can be made. This is the element analyzer where all the organic type of or the sedimentary work is done. the CO2 is produced and passed here. And this is the IRMS stable isotope machine. And this is the carbonate hydrolysis system. For any inorganic sample, you have to drop acid to take out the CO2 and send it to here. So this is a combo of 4 instruments actually. It works together. And this is a sample preparation unit. Cost wise, why it was important for me to have first sample preparation, because with the sample preparation you can do all the R&D work and the research work, even though you don't have your own AMS, because if you have graphite produced, anybody will measure it. Anywhere you can send. They have to just load the graphite and do the measurement. Nothing great. The major thing is here. But this system, the actual cost of the AMS is about 25 crore. But this system itself, the sample prep unit itself is about 5 to 6 crore. So I felt that it should be our beginning step. And in particular, I can tell you, we made a provision here to put a IRMS in line so that any sample which is combusted here, let's say 100 atoms of CO2 you produce, so 90 will be sent here for making the graphite. That means making carbon 14 measurement by AMS, and 10 atoms of CO2 will be sent here for making delta 13C. I showed you in the beginning, carbon has another stable isotope called 13C, and 13C by 12C ratio is very important for correcting the fractionation. And also the delta 13C is also very good tracer for several examples that I can come back to. And this means this setup measures not only carbon isotope, stable isotope, but also nitrogen and as well as sulfur. So it had another advantage. And with all this, in very short, I can show you, we did some very thorough testing of our sample preparation with the standards, with the blanks and all those things. And all those exercise we checked by going to Inter-University Accelerator Center in Delhi, as well as to PRL later on, where they had the AMS actually, which we don't have. But our sample preparation facility was very good, and we did very thorough test, which you can call quality test or quality assurance test. So that is why all this work we published in a very good international journal in 2020. So now I am coming back to this. Some other kind of samples like bone and teeth, which if you want to do, if you want to date, you have to do some chemistry in this. So in teeth, you have to extract the enamel part, and in bone, you have to extract its collagen part. If the bones are well preserved, then only the collagen will come. We have preliminary diagnostic test using the carbon and nitrogen isotopes and C/N ratios. You can check the quality of the collagen. And this yellow thing which you are able to see in this, from this bone, they have been extracted. These are the type of bones which are available from the archaeological field. Sometimes you get some paintings in the rock. We have not done yet this work, but if they are, I'll come back to this. This is doable by AMS, but protocols have to be set up. So what I mean to say, AMS offers plenty of other applications for dating so-called exotic samples, which we normally cannot date by any other method. But for each and every type of sample, let me tell you, you need to establish the proper protocol, chemical protocols, and you have to do very thorough testing. Otherwise, you can go way off wrong. Because as I repeat, here you can date even 0.1% of the carbon. But this 0.1%, if you are going that much low amount of carbon in a sample, then there is enough chances maximum chances you can go wrong because you can have contaminations. So this is the major concern. Some other utilizable tools you can see in this slide. What we do, our student Nikhil Patel, he has developed now. In our lab, actually, BSIP was known for archaeobotany for a significant amount of time, and uh, Dr. K.S. Saraswat and then Dr. Anil Pokharia are leading this group, and they are doing wonderful work by looking at the botanical grains, which are often found in any archaeological field in form of fossil seeds, which are burned. They are called char seeds. But we were not doing anything in archaeology related to bone and teeth. So I envisioned that we should also do zoological work. So that's what we did in this all 3, 4 years, 5 years. And using this small setups like Dremel kit, centrifuge, mixer, vortex mixture, heater and shaker, microcentrifuge, lyophilizer. These are all costly, elements. Altogether, if you compound all these things and put it into the money basket, this all will be more than something like, let's say, 20 to 30 lakhs. So this investment also we did along with the instrument. And more importantly, we started this work with some good archaeologists, and now archaeologists are also very happy to say that they contact me from all over the India, that at least somebody is doing this kind of work. So from very small pieces of wood, you can extract the cellulose part in this, and cellulose is the ideal subject, the base of the dating. You don't have to depend on the bulk wood dating. You can extract the cellulose, and then you are 100% sure that you are dating the arming material from the wood. Like in any tooth, you can separate the parts of the teeth, and then you can take out the enamel, because enamel is the hardest part of the teeth, everybody knows, and that will tell you very reliable age sometime. Bones also sometimes can go wrong if you want to date them, because they are very prone to contaminations. So all in all, now BSIP's modern radiocarbon dating facility is capable of measuring stable isotopes of carbon, nitrogen, and sulfur. Along with, we are able to process the samples of teeth enamel, wood cellulose, organic residues, and some small amount of microfossils like foraminifera, some small husk we have dated. And let me tell you this, in the macrobotany, one grain, one wheat grain, wheat everybody knows, barley or rice grain. Even in the burn, if you have a burnt rice, half of the grain is enough for dating. That much low easily you can go. So here I have shown, even though we are not that old with all this setup, we have been working with a lot of archaeological sites like from central India, Ubali, Vidarbha, Sonali, 4MSR, or Minjor from Rajasthan, Khirsara, Gujarat, Vadnagar. We are actively working since 2016. May, again, we are going for a conference. So we are getting good amount of sample and variety of samples, very challenging. And one or two only slide I can share with you, like from megalithic sites. People who know what are the megalithic sites, they may know, but just for all other purposes, this kind of encircle portion you get if you travel in the central part of India or southern India. They are called cairn-shaped megalithic burial site. It is assumed that some burial was there, but sometimes you don't get burial or very poor state of burial. So like two burial sites in Vidarbha region of central Maharashtra. What we did actually, we got what we thought of, because these megalithic sites are not properly dated in India. So fortunately, I would say, we did not get enough material or good material, any material from the human burial as per se, but what we got, the horse sacrificed along with the that person. There was, I don't know, uh, you people may know, some people may know कि एक ट्रेडिशन था इंडिया में, अभी तो नहीं है, कि with some auspicious people, उनके साथ जैसे वॉरियर्स, जो ग्रेट वॉरियर्स थे, उनके साथ में उनका जो घोड़ा था उसको भी सेक्रीफाइस कर दिया जाता था. तो we thought of, because these horses have bigger teeth compared to humans, so we thought of dating the horse and assuming that if we can date the horse, we can date the human. That is when it was made. And interestingly, from the surrounding soil, the horse teeth date, and the burial pots, near the burials, a lot of food items are kept in the, वो जो मिट्टी के बर्तन होते हैं उसके अंदर रखे जाते हैं, खाने की मटेरियल ज़्यादा होते हैं, फूड ग्रेन्स होते हैं, बट जब हमको मिलते हैं आफ्टर thousands of years, they all become soil type of thing. But we dated them. So these dates matched quite well, and they were much younger compared to the host soil, which I can show in the next slide. This slide shows what kind of radiocarbon dates we got from this fossil teeth. Okay, so this work is almost getting accepted now, in final stage of acceptance in Radiocarbon journal. I hope soon it will be accepted. This is all new work. We had really very tough time to get it accepted because a lot of questions are there. How do you know they are sacrificial horses, and why do you think that these horses were sacrificed along with the burial? Somebody can do this, that. So many questions are there. Anyway, so first part of my talk is getting over now. So here is the outtake of my talk, that now BSIP, which is also serves as a national facility for radiocarbon dating since 1974. From the conventional radiometric method, we are moving towards the AMS dating, which is very much needed. And towards this step, we have already set up the sample preparation units. We still have, we still don't have AMS at BSIP, but we are very happy to share that we have fully working sample preparation facility, which is capable of doing any, pre-required R&D for any specific type of sample. Then using AMS, maybe some 10 minutes more I will take. I think I can get this much of time, not much. So if you have your own AMS, why do you need AMS? Because if you have your own AMS, you can do some very interesting and exotic type of samples. You can try at least, and you can try to date them by AMS. That's what this paper I'm giving. I mean, so many papers are there, but this person, AJT Jal, is the very important and famous person because he's chief editor of Radiocarbon journal, and he's major person from the radiocarbon community. And one of the example in one of his paper, he has given this kind of book was dated by AMS radiocarbon method. And this book, as you can see here, the book of Isai. This parchment is on the display of shrine of the book in Jerusalem, and it dates back to 250 to 130 BC according to radiocarbon dating, which matches very well. You can see 150 to 125 BC from the studies of writing style. So the challenge here in dating this kind of, the books or the written material is, because from the written material, if the language is decipherable, you already know the date. So archaeology actually works very in hand to hand, hand in hand with the radiocarbon dating method, and both work in a symbiotic way, because radiocarbon dating provides the scientific chronology, but as well as sometimes with the archaeological objects, you can correct your methods because you already know the dates. So that's what happens. Some other example, these are really exotic, works where you can apply carbon 14 dating for inorganic pigment for absolute dating of paintings. So if you get this old, you know, wall paintings, and if you have some organics, I'll show you here what you need. You can date wood, you can date canvas, or you can date natural binder. And it has been found in this paper that you can use the carbon 14 to date 14th to 16th century wall painting. And since these paintings were done on the lead white, which was the greatly used by greatest of artists. So these kind of applications we have not done, but what this is required, you need, a dedicated AMS for this kind of work, as well as a dedicated sample preparation laboratory, and there is a will to do it. Even if you have both sample preparation unit as well as AMS, if you don't want to do it, you can easily neglect, or you can easily say, no, I don't want to do this, because these type of samples always, come with a challenge with your lab, with your staff, their skills and their protocols. Because no matter how much you are professional, every sample will challenge you in terms of your technical prowess, that you need to, recheck, double check, or sometime totally change your protocols. Sometimes, these are little easy, but not very good examples, but I have just taken some, the first author at the end. In this paper, I was one of the reviewer, and I was not very happy with this paper, let me confess with this, but even though this paper got published in +1, they dated two parijat trees from India, old this baobabs they call it, and the idea of dating AMS radiocarbon dating of these trees were this. They try to go to the girth of this old tree, parijat tree. I think everybody knows. They are very auspicious. Some people call them as they have come from heaven or something. So they got dates 779 plus minus 41, 770 plus minus, means according to their estimates, these trees are not that old. They are only 700 to 800-year old. But this dating, I doubt. The reason is you don't have any control on getting the right kind of the girth, and these are called, the upper bound ages, because it may so happen if you date some other sample from much more inside, you can get older age. We don't know. Dating the tree is really challenge, but you can try. And this is very famous or infamous example of application of AMS. I'll come to it little later, but first I just summarize that some of the most interesting applications of radiocarbon dating involves sometimes very controversial archaeological finds, ancient documents and textiles. So that's why I was telling this is a really a challenge and sometimes threatening to the radiocarbon community when they meet this kind of objects from archaeologists or conservationists or some, direct public museum. Because if you are not sure, no matter how much um, you are good in your chemistry, but that particular object can challenge you. And that is what exactly happened while the Shroud of Turin. It's a famous thing. It's the most, you can say, costliest thing in the world. Why? Because this is nothing but, here I have shown the picture from Wikipedia, Google, you can see it. But this cloth is believed to have the blood stains of Jesus when he was crucified and buried. But in 2010 onwards, this small pieces of this cloth was distributed among 3 top labs of accelerator mass spectrometry around the world. When they dated it, everybody, all the labs dated and produced the radiocarbon age which were coming around 1400 AD, which was totally off. It should have come at least 0 CE or maybe 1 BC or something like that, because it is believed, I mean, everybody knows historical Jesus, and it is the cloth belongs to him. So after this dates came, lot of controversies came. At least 26 papers got published, and believers do not believe the AMS dates. It may so happen that cloth was replaced, or some bacterial action happened in the cloth. We don't know. This is still a matter of controversy. But in this time, Shroud of Turin could not be rightly dated by AMS. Okay. Some paper, now I'm shifting from radiocarbon dating to what you can do in general with the natural aging of paper, because INTACH works on this protecting and securing and conserving the old documents. And the very interesting paper, only one paper I have kept it in my talk. It was very interesting to me also, why I have chosen it, because all those exercises which are mentioned here, and it is very recent paper, I would say 2017 only. In this work, using simple chemical methods, and um, I think everybody's laboratory has those kind of equipments, and to check the physical properties and chemical properties, and you can determine the natural aging or the antiquity of a paper. And in our lab, our colleague Dr. Anjum Farki has, for example, this light microscopy equipments, very fine, very state of the art, you can say. And this kind of studies can be undertaken, which are very simple to do compared to the AMS radiocarbon dating. You can determine the fiber composition and look at them at the Nikon light microscopy. And after, what you have to do, you have to just soak the paper in the water, allow it to swell first, maybe a couple of days or so, and then you have to stain it. There are several staining agents are there, like safranin, iodine, depending on the protocol, or what you want to do. Like if you suspect like the paper is made of a lot of starch, you have to stain it with the safranin, and then you can look at it under the microscope, and this type of pictures you will see. And from this information, I'm not the expert of it, but people who are expert in our BSIP, a lot of people are expert in looking at these pictures. They can tell you the whole know-how, or what you call nitty-gritties of this paper technology. Okay, so my purpose is just to show off here. I'm not the expert of this, but this is all doable. Some of the chemical analysis which they have mentioned in this paper, they are very much doable with our lab. So paper documents, they have tried to look at, and one important thing what they found, if you look at the papers from early 18th century to, let us say, today, the pH values have gone up, means from acidic values we have come up to slightly alkaline values, and this depends on this alkalinity value of the paper, depends on its essentially the composition, this glucose, polocellulose, lignin, all this. Even today in our lab, all these biomarkers you can measure, you can easily measure. They are very, major biomarkers. Lignin, everybody knows, it's a refractory organic matter. So what they found in this paper, that with the advancement in the technology of the paper making, nowadays we are making very alkaline kind of paper, but earlier when the paper was not there, sometimes people used to write on papyrus, or in India what we call betula, or bhojpatra. actually some leaf. So those kind of material can be looked in, and you can do a lot of physical and chemical tests also. You can measure its organic geochemistry, organic chemistry, as well as like ash content, its tensile strength. All those things you can do in your lab very easily. And moreover, on the top of that, you can date the paper if papers is datable, and very small amount is needed these days, like 2 to 3 or maybe one punch of 1 centimeter diameter, like what you call cover of your paper, cover of your pen. If you the cap of your pen, if you take out and you put it on a piece of paper, sometime that much amount of paper you can take and take to your laboratory, and you can date it. So with this, I thank you all for your attention, and I sincerely thank again INTACH for providing me this opportunity to share our lab developmental works. To be very honest, we have not done much work with the exotic samples. The reason is exotic samples very rarely anybody gives us, because there is a chance of losing it. They are very precious, they are very important. Like paper, many people approach us, but they don't want to lose, because when I say that it may be dated, may not be dated, we can go wrong also, they say no, no, don't waste my paper. But for advancing in this kind of thing, you need samples to set up your protocols. Okay, so with this I stop here, and some of the questions, if I can take, I'll try to take. If I know them. So Padmaji, can I go to chat box?
Thank you, Dr. Agnihotri. There are a few questions. I'll just read them out to you. The first question is from Shubham, and he's asking which kind of bulk sediments are ideal for carbon-14 or AMS dating technique.
Okay. Bulk sediment means just sediment must have some organics in it. If the sediments are sandy, then there is no organics, then they are not datable.
Mr. Shubham, you are there?
They should have organic matter produced in situ.
Okay. And then?
Hello.
Yeah. Mr. Shubham, if you can
Yeah.
have a discussion on
Yes,
that.
sir.
Yes.
So if I have archaeological deposit dated back to prehistory, so there are very rare chances, especially in Indian context, to getting this kind of settlements like organic deposit in prehistoric deposit. So what could be the methodology to get that?
If you have enough amount of samples, they can be dated by even with the liquid scintillation method. You need something like 50 gram of sediment, and we can check the carbon content in that. And if the organic the carbon content is good, then it can be dated by radiometric method as well as AMS method. It involves only very less amount of sample. The important thing from the archaeological thing, if you are talking about, because I'm not able to listen to you very properly, you need to find, if possible, the charcoal layers or the burnt layers, and if the woody material is burned, that kind of sediments are ideal for dating.
The presence of carbon.
Yes.
The more the presence of carbon, the more.
Much better.
Yeah. I hope, Shubham, that answers your question. The next question is, is AMS dating or carbon-14 dating useful for metals too?
No. As I said,
very common
radiocarbon dating actually provides you dating of the death of the object. And metals don't have life. Yeah. They don't respirate. They don't exchange carbon.
Yeah. So there is no way we can use this for dating any kind of metal. So,
No, it is not applied to metal. It is only biogenic dating. This is purely biogenic dating.
yeah. The next question is, I have, this is again Shubham. He wants to know, he has colluvial origin ferricrete sediment deposits associated with middle Paleolithic stone tools. Which method is ideal for dating these kind of sediments? Colluvial origin ferricrete sediment deposits associated with middle Paleolithic stone tools.
To be very precise, I don't know what is colluvial origin ferricrete or sediment deposited on. I am able to get only this middle Paleolithic stone tools. But this could be a research subject. You have to look at them and take it to a lab. As I guess, I want to ask Shubham that what kind of date you expect from this? Then the method
Sir,
can come.
yes, sir. So they are middle. Sir, are you able to hear me properly?
Yeah, I'm able to hear you, Shubham. Please go ahead.
Yeah. So these are middle Paleolithic. Middle Paleolithic is yet not well dated in Indian context, but related with Atira
So
Pakkam
years,
context.
how many thousand years? They are 20,000 years, 40,000 years, 50,000 years.
No, sir. Actually, they are even back than 50 to 75,000 with the reference of Atira Pakkam dates. So they could be dated back to 50 to 75 or even 80,000 years.
No, then they
But
cannot be dated by
they
radiocarbon.
cannot. Yeah. That is my question. That they are even beyond the limit of radiocarbon dating. So
Yes.
what? And we don't have in Indian context. We don't have that much organic material with associated.
You insert a pipe and you do OSL dating, optically stimulated luminescence dating. BSIP also has, Vadia also has, a lot of labs have this these days OSL dating. That gives you the last burial history. You know, that material got buried and when it saw the sun last time. That's not a biogenic age, but you can get its burial age by OSL dating.
Okay, sir. Thank you, sir.
Okay.
Thank you, Dr. Agnihotri. I don't see any other question. Okay, there's one question. It says, what is the minimum time frame for which dating can be done? Can we date a material which is 100 years old?
Tough. I mean, you can say radiocarbon with the radiocarbon method, last 200, 300-year-old, we dated, in fact, actually one boat which was recovered from the Chhatar Manjil, the earlier CDRI office of this thing, our Lucknow. We dated, we got more or less right age, 270 plus minus 40 year or something. But last 200 year or 300 year is not a very good time span for radiocarbon. The best time span for dating the radiocarbon, you know, by radiocarbon method, the best time range is 300 year to 50,000 year or 40,000 year.
Okay. And any other questions? I don't see any. My only thing is, what is the range, sir? If you're dating something, this is a question, a follow-up question. You said 100 years is difficult, but even when you date, there is plus minus that you said.
That is called uncertainty.
Yeah, that
Every
is.
dating method has uncertainty with it, involved with it. And this is a good question. I thought somebody will ask, somehow I missed it. Actually, the radiocarbon dating method is the only method, that is why it is most reliable and most famous, which can provide you, by calibrating it, the calendric ages, because no other method, like other methods I mentioned, OSL, etc., they are some other kind of, burial ages and all they provide. Radiocarbon has important, very important issue, because it provides you a biogenic age, and then the age which you get by dating it, you can calibrate it by some norms, by tree rings and then corals and etc., etc. So you get actually the calendric age. Are you getting calendric age? Like Today is 29 of March 2022. So people want to understand, if you have dated an object, that how old is this from today. Okay, this is called calendar age. So by historical reasons and the convention, the radiocarbon ages are expressed in terms of BP, before present, and before present means 1950. Any AD date which is we produce, we hinge it with respect to 1950 wood, in fact. And then because of the methodology used, like liquid scintillation, it has a different methodology. In AMS, we have different methodology. When you are counting the atom or you are counting the decay, uncertainty is always involved with everything. So when you report some date like 530 year plus minus 34, so it essentially means the date of this object is, listen to me very carefully, 530 plus minus 34. So you can say 500 to 66 something, the total time span. So scientifically, what we want to say, we don't say often because we understand this language very, very well. But for all other general people, when we say the date of this object is 530 plus minus 34 year, it means 95% chances is there that the date belongs to between 566 to 500 years. This is the mathematical language. We don't claim, we don't commit that it is like really 530 or 534. We can't.
Okay, sir. Thank you. Now, there is a lot of interest for dating methods for metals. If you could just suggest what are if there are any dating methods for metals, copper alloys, height in bronze. A lot of people have put in this question. I understand it is not radiocarbon dating, but could you suggest any other dating method?
I'm afraid that for dating this metal and alloys, they are contextual. We know already that this kind of people, like there's a Bronze Age of Harappans or Indus people, they were making this copper alloys. So I would say, along with this, where you get these objects, you get other, you have to look at other objects also, like microbotanical stuff, some particular food or grain. If in that pot you can get some organic residue, you can get that can be dated, but the copper cannot be dated.
Yeah.
Same as long as I know, metal cannot be dated.
Yeah.
I mean, we have not done much. I mean, not me means not the whole world has kind of done this work that much, but nowadays this technology has not come even in the, I would say, US or Europe much, where you can measure the copper isotope or zinc isotope. If you can measure them, like in Caltech people measure, maybe some, but not for dating. But those isotopes can be utilized for knowing the provenance. Provenance means this copper has come from where. Okay, because in the Khetri, like Rajasthan, you have some copper ores, and some copper, you can say, might be coming from Balochistan or Iran. They may have different sources of copper, and isotopically you may trace them. But as I said, when you ask, I mean, if archaeologists ask that I want to date this particular metal object, I always ask them, look at something else which you got along with it. Like in a metal pot, if you have got some organic stuff or some organic residue, some leaf, some grain, those can be dated. So contextual date can be provided. Okay.
Thank you, sir. I think those are the questions. We don't have any other questions.
Okay.
So thank Thank you very much. Mamta ji, if you can.
Yes, yes. Thank you very much for giving us your valuable time and give your very informative presentation. In future, INTACH and BSIP collaboration, if possible, for carbon dating and fiber analysis. So thanks once again, sir, and also who have joined this presentation. Thank you very much. Thanks.